Substitution and elimination reactions of alcohols. We've been talking about this in class, and I just wanted to give you a review to go over the 5 key reagents and reactions that we've been talking about recently. So the key concept that we're thinking about with reactions of alcohols in substitution and elimination is that we need to turn OH, which is a poor leaving group because it would leave as OH minus, into a good leaving group. We need to turn it into water, turn it into some other leaving group that's going to be able to leave so that we can then do a substitution or elimination reaction on that. We have some key reagents that we're thinking about here: tosyl chloride, PBr3, SOCl2, HBr/HX, HCl will work, HI will work, and sulfuric acid. So I've listed out just some example reactions on this chiral secondary alcohol, so we can see what things are possible. When we think about tosyl chloride impurity, and that's a reaction that many of you are doing in lab, that's a reaction to turn the OH into a tosylate. Again, remember that there's a structure for a tosylate, so when you see tosyl chloride, don't forget the structure of that. Is paratoluene sulfonyl chloride. There are some elements, some structure that goes with the TS, and that's a way to convert the OH into a good leaving group with retention. This will work for any alcohol, and this mechanism that we'll go over in a minute is like a carbonyl substitution reaction of an acid chloride. We'll see what I mean in a minute about that, but it will work for any alcohol. PBr3, you'll see, converts the OH into a bromide with inversion. With inversion tells us this is an SN2 reaction. It will work for only primary and secondary alkyl halides. As we know, we're not going to be able to do an SN2 reaction on a tertiary alcohol. Sorry, I said alkyl halides, alcohols. Thionyl chloride, same deal. We get inversion, it's an SN2 reaction. It's only going to work for primary and secondary alcohols. Right? Tertiary alcohols will not react with thionyl chloride, SOCl2, or phosphorus tribromide, PBr3. When we look at the 2 acidic reagents, HBr and sulfuric acid, HBr, something weird's going on over here. We see that we get what looks like an SN2 reaction here, and then that product is a little bit strange. That is an SN1 reaction, and we have a carbocation rearrangement going on. All right, so that's a little bit weird that we get a combination of SN1 and SN2. This in general is much more useful for primary alcohols, where we get SN2, or tertiary alcohols, where we get SN1. You can see in this case we get a combination of SN1 and SN2 for a secondary. Right? And then sulfuric acid is completely different in that we're not getting substitution at all. We're getting an E1 elimination for sulfuric acid. Right? This is a really interesting case because it's the only one of these reactions that directly will give us an elimination. These other ones, you can do eliminations after you turn the OH into a good leaving group. Here we get E1, and we know that E1 goes through a carbocation, so that one's only going to work when we can form the carbocation, so this works for secondary and tertiary alcohols. Okay, so let's go through some of these mechanisms so it's clear what's going on in these reactions. So we'll take them one at a time. So if we look at the reaction with tosyl chloride, again, it's really nice to remember what the structure of a tosylate is, right? And so that we can do the substitution reaction. And again, we're just going to have the alcohol attack. And this looks much like a reaction. If this were an acid chloride, it would be the formation of an ester. In this case, we're doing it to form a sulfonate. All right, so what do we get? We get that intermediate, and again, just like if it were an acid chloride, we can reform the oxygen S pi bond. Cl can leave. And all we have to do now is remove the proton and we get to the tosylate, right? And that's why these reactions are generally run with pyridine, so that pyridine can act as the base, remove the proton, and then we have formed the tosylate. Sorry, I forgot that methyl group. We can form the tosylate. Right? And in general, we'll see these written as just OTS. Right? And the key part of this reaction is that this happens with retention. Right? And hopefully it's clear why it's retention. We never broke the carbon-oxygen bond. Right? So very useful reaction to make a tosylate. All right, let's erase, and then we can do the rest of these reactions. All right, so the PBr3 reaction, phosphorus has 3 halogens attached to it. It's going to be an electrophile, electron poor. The oxygen of the alcohol is going to be the nucleophile. It will attack the phosphorus. One of the bromines will leave. We've turned the alcohol into a good leaving group. We have Br-, which is a good nucleophile. That can come and attack. And we get the oxygen to leave. This is definitely an SN2 reaction, so this reaction occurs with inversion. All right, so that's a very nice way to turn an alcohol into a bromide with inversion. Again, it's SN2. It's not going to work on a tertiary substrate. The thionyl chloride mechanism is similar. Sulfur is going to be a great electrophile. The alcohol oxygen is going to be the nucleophile. And this reaction also should remind us of a reaction of an acid chloride. Reform the pi bond. Chloride can leave. Chloride now is the nucleophile that can displace the oxygen, and that gives us our inverted chlorine. Right, and again, this is our SN2 reaction where we're getting inversion, only going to work for primary or secondary alcohols. When we look at this reaction with HBr, we can see that there are 2 possible mechanisms going on, as we mentioned previously. The alcohol is definitely going to get protonated. And some of the time, the Br- is just going to displace water in a nice SN2 reaction with inversion. But sometimes, we'll take that same substrate. The water is just going to leave to give us a secondary carbocation. At this point, we can have a hydride shift. To give us our planar tertiary carbocation. And at that point, the Br minus can add, giving us a tertiary bromide, again, after the rearrangement. So we have an SN2 reaction. Down here we have an SN1 reaction, all right? And so it's important to remember with secondary, we're going to get a mixture of these things. If we have a primary alcohol, so if we have this alcohol with HBr, this is going to be SN2 only. Right, so for a primary alcohol, it's going to be SN2 only, right? And if we move back up to the top, if we react this with a tertiary alcohol, it's only going to be SN1. Again, forming the tertiary carbocation. Now Br minus can add. Okay, so just remember with HBr, we have to be very careful about what kind of alcohol we have to tell us what kind of mechanism is going to take place. Right, and then finally, let's look at the reaction with sulfuric acid. We're going to protonate the alcohol. The counterion for sulfuric acid is not a good nucleophile. Since it's not nucleophilic, we don't have to worry about a substitution reaction. So instead, we're going to form a carbocation, just like we did with the HBr reaction. We're going to get a hydride shift to the tertiary carbocation, and then we're going to form the most stable E1 product that we can. We have 3 beta positions. 2 of them are identical to form the most stable tri-substituted alkene, right? And so that's what's going to happen, is that we're going to have an E1 reaction to form a tri-substituted alkene. Again, if you pull off the beta protons there or up here, you're going to get the same compound because those things are equivalent, right? And we're going to form the more stable tri-substituted alkene. And again, by an E1 reaction for sulfuric acid, right? So always remember with sulfuric acid, it's going through a carbocation, secondary and tertiary alcohols. It's not going to work for primary alcohols, right? So secondary and tertiary alcohols, right? So these are 5 useful reactions of alcohols when we think about how to do substitution and elimination reactions of alcohols, things we're going to use all the time.